Lights down low?
Yes.
How's that, guys? Is that about right?
Yep.
I don't know if you can give it. Yeah, that's all good. Hey, welcome, guys. Thank you very much for coming out on a wet night. So let's get underway. So this beautiful picture of the night sky, absolutely gorgeous, was taken from Paranal in the Atacama Desert in Chile. Beauty, you can see here the Milky Way galaxy spread out across here like this. I've actually got a new pointer. If it doesn't work properly, I'll change. But you can see that the nice dark dust lanes here in the central bulge of the Milky Way galaxy. Looks nice. Can anyone tell me, knowing that it was taken in Chile, looking back towards the central bulge of the Milky Way, who can tell me what time of the year that was probably taken, that it would have been taken? Winter time, yeah, absolutely, June, July. I'm just going to change over my pointer. Just means the people online can't see the pointer, but this is far more reliable. Okay, yeah, absolutely. So it was taken in the middle of the year, and you'll find out why shortly in the talk. And when you look at beautiful images like that, you can't help but in awe just think to yourself, wow, that's our Milky Way galaxy. How big is it? What is the structure of it? How do they know all this stuff? How did they learn about all this stuff? And that's why tonight's talk is titled The Milky Way, Our Home Galaxy, where together we're all going to go on a journey through time and through the history of the discoveries and what we now know about the Milky Way galaxy. So I've split it into 3 chapters. We'll talk about galaxies in general and the types of galaxies. Then we'll talk about the anatomy of the Milky Way, and then we'll wrap up with a bit of a summary. So, types of galaxies. First of all, there's 3 types of galaxies, but first, what is a galaxy? Galaxies essentially are collections of stars and their associated objects like black holes, neutron stars and white dwarfs, plus gas and dust, dark matter as well, that are all gravitationally bound in a large collection. And as for stars, you can get millions, sometimes billions of stars in these gravitationally bound collections known as galaxies. A good analogy would be that if stars or other objects were buildings, the galaxy would be a city. There's a good analogy of imagining what a galaxy is, except gravity holds it all together as one collection. So there's 3 types of galaxies. There's spiral galaxies, elliptical galaxies, and irregular galaxies. So looking at spiral galaxies first, they make up about 60% of galaxies, and indeed our Milky Way galaxy is a spiral galaxy. This is just an artist impression of one here. Of course, we can't take a picture of the Milky Way galaxy because we live right in the middle of it. It'd be like taking a picture of your house and garden from inside your bedroom. Can't be done. So you can see here, it's a flat rotating disc, or flat disc, much like a dinner plate or a pizza, if you will. It has these appearances of these spiral arms, which we'll talk more about through the talk. And then it's got this nice big central, very intense, bright central bulge in the middle. And 2/3 of spiral galaxies have this sort of central bar structure through the middle, which once again we'll talk about. So those are spiral galaxies that make up 60% of galaxies, and our Milky Way is one of these. Okay, and the next type of galaxies is these elliptical galaxies. And essentially, they are smooth and they are essentially featureless. As you can see here, there's no spiral arms, there's no big central bulge going on or bars. They're very, very featureless. They're ellipsoid sort of shaped. Dimensionally, that looks like a rugby ball is the best description of elliptical galaxy in terms of its shape. They're known as being red and dead. Red in that they are very old stars, well-evolved stars that they're full of, and older stars like your red giants and your red supergiants and so on, they have a red appearance. So the whole galaxies tend to appear red. And dead refers to there's no star formation going in them. All star formation has all happened and gone. So they're often called red and dead. So how do they get like this? Well, they're usually the product of galaxy mergers. And you can see here 2 galaxies, 2 spiral galaxies that are merging, colliding together. And typically when you get that, all the dust and the gas comes together and you get this real frenzy of star formation, also known as starburst. And through that process, all the gas and dust gets consumed, forms into all these new young stars, and eventually an elliptical sort of shape starts forming of old stars as the new stars die out and all the gas and dust has been consumed. So that's how they end up being that way. Where do you find them? Typically you find them at the centre of galaxy clusters. Galaxy clusters refer to just as galaxies are gravitationally bound collections of stars and so on. Then galaxies themselves are grouped together into what they call clusters and gravitationally bound, numerous galaxies. So typically you find the elliptical ones in the centre. They come in a wide range of sizes. Your spiral galaxies tend all roughly to be sort of in a certain range, as opposed to the elliptical galaxies. You can get dwarf elliptical galaxies, middle of the range, and then you can get giant elliptical galaxies. So they come in a wide range of sizes as opposed to the spirals, who tend to fit in a sort of a range of certain range of sizes. Okay, now the third one is irregular galaxies. They make up about 20%, as the elliptical ones do, of galaxies. This here is a Hubble Space Telescope image of an irregular galaxy, and you can see there's no distinctive regular shape. There's no spiral or disk structure. There's no football shape, elliptical galaxy shape there. There's no structure to it or any smooth appearance. They're just literally that, irregular galaxies. And they're typically very small. Their composition is usually a mixture of young and old stars, and their fate, eventually they tend to form they end up as being satellite galaxies of much larger galaxies, and they eventually merge in with those larger galaxies because gravity is just, they're small and they're next to something much bigger, and they tend to just get eventually merged in and cannibalized by larger galaxies. So those are your three types of galaxies. Okay, so let's now look at the Milky Way galaxy, and this is going to be where we start our story of discovery of the Milky Way galaxy. And this is what it looks like in the night sky, and you see these beautiful images here and all these dark, thick, dense lanes of dust that block the light from behind it, and that's what you're looking at when you're looking at the night sky. Okay, so why have we called it the Milky Way? Because up till the invention of telescopes, it just looked like a big blur of spilt milk, big white blur across the sky, so they called it the Milky Way. Fair enough. But it was Galileo in 1610 who first got the telescope and pointed it up, and he was the first guy to have the insight to realize it wasn't one just big blob or object. It was actually billions of stars that just happened to be so far away from us that with the unaided eye we cannot resolve them. But with a telescope, you could suddenly resolve individual stars. It was Galileo who did that in 1610. So that was a significant step forward with the history of what we know about the Milky Way. Then this guy here, British astronomer William Herschel, who built himself built himself a large reflector telescope, which he was very much into at the time. And he then measured the brightness and the distance to almost every star he possibly could. Thousands of stars, catalogued them, and that enabled him to bring up some sort of better grip of what the Milky Way was like. And he concluded that, it was an increased density of stars in this big flattened disk here with this big bulge in the middle. So they weren't just random stars that happened to look that way. He worked himself out. You might think that's obvious to us today, but it wasn't obvious at the time. He was able to deduce that indeed this is the Milky Way here. It's just a flattened disk with a big central bulge. That key thing really laid down the foundation for our understanding of the overall structure of the Milky Way in the future. So that was a very important thing. Okay, so this is an image here from the Hubble Space Telescope of Andromeda Galaxy. It's our nearest spiral galaxy to us, nearest large spiral galaxy. It's about 2.5 million light years away. 1 light year being the distance that light travels in a year, which is 10 million kilometres. That's 2.5 million of those away from us. So that's the Andromeda Galaxy. It's a little bit bigger than the Milky Way, but we love using this image to imagine what the Milky Way spiral galaxy would look like from a distance. So that's why we use that there. And you can see here the nice big disk that it is in this big central bulge. And so you can see that William Herschel was quite correct. So where are we in here? And in typical fashion, before modern science came along, we were always considered bang in the middle of everything. You know, we were in the middle of the universe in the early models. Then we were in the middle of the solar system was in the middle of the Milky Way, and so we always had to place ourselves bang in the middle. So that's where we were until 1918. And then along came this guy here, Harlow Shapley, and from 1914 to 1918, he studied globular clusters. Globular clusters are these things here, sort of collections of millions of stars. They tend to be old stars, tightly gravitationally bound together in quite compact sort of arrangements. And they're called globular clusters. The Milky Way has got about 180 or thereabouts, quietly, very slowly orbiting around the Milky Way, which we'll look at closely. But he thought, well, let's have a look at these globular clusters. And he said he was going to measure the distance and the positions to 60 globular clusters. And he quite rightly concluded that if that's the Milky Way and you've got all these large blobs, these globular clusters, it makes sense. If they're all in an orbit and arrangement, they must be centered on the center of the Milky Way. It just made sense because everything is centered on the center of everything. That made good sense. So he got actually 69 globular clusters above and below the galactic plane, and he observed indeed they were arranged in a spherical formation, but they weren't centered on us. That was a biggie. They were centered on the constellation of Sagittarius and Scorpius in this region of the sky here. So that was the first thing that there is clearly the center of the Milky Way, not where we are. So that was another big milestone in us learning about the Milky Way galaxy. So here's a nice little diagram that I've just knocked up here. So here's the central bulge. Here's your flattened disk that we've got here. The sun now, we put ourselves out here, out in the suburbs. We'll talk more about exact distances in a minute, but here's all your globular clusters out here. This region that they are in here is called the galactic halo. And the galactic halo is a region here, a spherical region that surrounds the disk of the Milky Way, and it's got your globular clusters, and it's just sparsely populated with old stars, predominantly old stars, and that was what they call the galactic halo. It's a spherical arrangement. Okay. Now, Harlow Shapley, when he did his calculations, in typical fashion, he was very, very good, and he came up and deduced the right outcome was correct, but often their actual measurements were a little bit out. Why were they out? Because of these thick lanes of dust that are obstructing the light coming through from distant lights, and he didn't quite calculate that in. But his principle was right, that the center of the galaxy is exactly where he pointed out it would be. But with time and better technology, we're now able to cut through the light of that dusk. There's two modern technology that allow us to map the galaxy. One is radio telescopes. We're going to look at these both in a bit more detail, but observe the gas in the galaxy. And the Gaia Space Observatory is able to observe most of the stars in the galaxy, certainly in a vicinity of our neighbourhood, very accurately. So let's look at each one of these. So the radio telescopes came in sort of 1930s, thereabouts, and have just got better and better and more advanced. And the relevance of them in looking at the gas in the Milky Way is, first of all, radio waves cut through dust. Radio waves are just longer wavelengths, lower energy and longer wavelengths of light. And they cut through dust quite happily. And the gas clouds are full of neutral hydrogen and molecular hydrogen. So neutral hydrogen is just one proton and one electron. And what happens is those subatomic particles have what we call quantum spins, usually up or down. And let's just for argument's sake, if the proton might be up, the electron typically is down, what they call anti-parallel, and that's a nice stable state. But just by chance, it's a very small chance, but just by chance, statistically it happens, the electron flips itself back up into a upward spin, and that's called a parallel arrangement. But it is unstable, so the electron flips back again to a downward quantum spin, and in that process, releases a photon of light with a wavelength of 120 centimetres, which is in radio wavelengths. And the radio telescopes can pick that up beautifully, and it's a wonderful tracer of neutral hydrogen in the plane of the Milky Way. Cuts through the gas beautifully, so you know where your gas is. The other major gas is molecular hydrogen, or H2, so two hydrogens bound together. That's relatively stable, and it doesn't really give out much radiation. But what happens is that bumps into a carbon monoxide molecule, and there's plenty of those around, because remember, second only to hydrogen and helium, carbon and oxygen are your next two commonest elements in the universe. So there's plenty of CO2 around, not quite as much as your molecular hydrogen, but still plenty. And the molecular hydrogen, the H2, collides, bumps into the CO molecules, and the CO molecule, the carbon monoxide, then does a little bit of a flip or a rotation and turns around a bit, and when it does that, it emits radio waves, and you pick that up. So your carbon monoxide is a very good tracer of molecular hydrogen. So it's those two phenomena that radio telescopes could pick up and quite happily map out where all the dust is in the Milky Way, where the gas is bypassing the dust. And it is from there they can map out the shape and the structure of the arms in the galaxies, those spiral arms, quite happily, but also the Doppler shift, and that's when something's coming towards you, away from you, the wavelength just gets changed, gets stretched out a little bit if it's moving away from you, or shortened if it's coming towards you. It's the Doppler effect. And measuring the slight change in wavelengths of the gas coming towards us or away from us, they can also then measure the movement or the motion of the gas around the galaxy as well. They've actually worked out from there that all the gas in the region around the sun is moving around the galaxy at about 230 kilometres per second, and that's how they get that figure, is from the Doppler shift of radio wavelengths, which means, and we'll show this later on, it's probably more easier to show later on, but you're probably wondering how long does it take to do a full circuit. It takes about 230 million years for the sun to do a full circuit around the Milky Way galaxy. So when we were here in this part of the galaxy last, the dinosaurs were roaming the planet, just to put it in perspective. Now the Gaia satellite, really high precision stuff, that was from the European Space Agency, was launched in 2013, and since then it's been sitting out at a gravitationally stable position called L2 Lagrange point, and that's a very a gravitationally stable point in Earth's orbit around the sun. Quite a few telescopes, most famously the James Webb Space Telescope sitting up there, so it can sit up there with minimal amount of fuel to adjust itself. It's not relatively stable. So it's sitting up there, and it's quietly and with high precision measuring and analysing the distance to stars, the motion of stars, the composition of stars, and that's very important because it's actually able to look in visual and near infrared. Just as you've got normal visual light here and the radio waves out here, which are longer wavelengths, we can't see, the infrared ones, once again, is just between the two. Slightly longer wavelengths, slightly lower energy, but our eyes can't see in the infrared. So it is able to see in the what they call the near infrared, the infrared part that's close to visual wavelengths. And it's able to form a very detailed 3D map of where all the gas is and the stars are in particular in the Milky Way galaxy. And it's able to trace, the Milky Way's structure, dynamics. It's able to measure the movements of stars, because every time as we rotate around throughout the year, it'll look at the same stars again and recalculate their positions and work out where each star has moved. But also I've put here the evolution, because it can also have a close look with the spectroscopy at the composition of stars. And if you get a group of stars of very, very similar composition, and you notice that they're all moving together as a group, of course you just go calculate backwards and you can see where groups of stars have come from, how the galaxy is evolving. And that is the method, that's exact stuff that they're using with the Gaia data. They're actually working it back through previous dwarf irregular galaxies that have actually merged, collided with the Milky Way, and have merged by seeing groups of stars that all very, very similar composition, and you can see them all moving together. So they calculate the dynamics backwards, and they'll tell you often what happened to the Milky Way so many billions of years ago in terms of mergers and collisions. So that's very, very important. Okay, so this is Once again, an artist's impression, looking down as if you're looking down on the Milky Way galaxy. It's what we know so far. So it's a rotating disk of stars, gas and dust. And you've got these sort of spiral arm appearance of active star formation going on here. And just to add a note, sort of the actual disk of the Milky Way is not just spiral arms all going around like that of material. It is a disk. That disk is full of stars and gas and dust. But you've got these spiral regions of increased pressure that are moving very, very slowly, rotating also slowly around the Milky Way, slightly slower than the stars and the gas are also rotating. So you might have a bunch of stars and gas and dust that's moving forward. They start moving into one of these spiral regions of increased pressure, and the increased pressure compresses stuff down, and all the gas gets compressed and triggers a whole frenzy of star formation. And when you get star formation, you get two things. First of all, you get new, large, bright stars that blaze away. You're starting to see them. And we're going to have a look at shortly what happens. You start getting nebula, those nice big pink areas as well. And they just stand out more. So you've got gas and dust and stars throughout this whole disk, but these spiral arms you're seeing are regions of active star formation, big, massive, bright stars and all these little pink nebula here that's going on, what they call emission nebula. So they're just more prominent, sort of spiral arms of prominence would be a way of calling them there. So that's a good artist's impression. You'll see that of the Milky Way. Now the next thing is, where do we fit? We fit in here, and we fit in between two of these spiral arms. So you've got your Sagittarius arm that goes along like this here, like that there, spiral arm. And you've got another one, the Perseus arm, and that goes out along here. It's another big major arm of the Milky Way. And there's a little bridge, or what they call a spur, between the Perseus to the inner towards the Sagittarius arm. And we sit just on the inside of that, about in the middle of that little spur or bridge, and we're just on the inner edge, right in there, and that's where our sun sits. And I'm about to show you shortly, that's about 26,000 light years, so it's about halfway out, but that's where we sit in the Milky Way. And a little, just on the inner edge, halfway along, a little bridge or spur between the Perseus and the Sagittarius arm. Now, we go round, of course, so I've just blown up the sun up a little bit here. Here's Earth, and of course, throughout the year, Earth goes round the sun like that. And this is getting back to that first slide I talked about, what time of the year that picture was taken. In the middle of the year, so southern hemisphere's winter, northern hemisphere's summer, we at Earth, if you look that way, you're just going to get blinded by the sun, it's daylight, but at night time, we're looking back to the centre of the Milky Way. And as we go around in our summertime, for the southern hemisphere, or sort of let's just call it December, January, we're looking outwards towards the outer part of the galaxy that way. So that's why our view of the night sky and our view of the galaxy changes throughout the year as we rotate around. Now, so this is just zooming in on our region here. Let's orientate ourselves. So there's the Perseus arm up there. Here's your Sagittarius arm long here. And here's the Orion spur. And here we are sitting just on the inner edge, halfway along that spur, and that's us here. The reason I put this into as close up, because these are some of the sights that you'll see when you're looking in the night sky, and you'll suddenly realise, oh yeah, that's where it is. And looking back this way, in summertime, of course, here is the Orion Nebula, very close to us here, the nice big red emission nebula, which we'll have a closer look at in a minute or two. The Rosette Nebula, probably a lot of you who do the night sky in summertime will be very, very familiar with that as well. So that's why we're looking back at summertime. Of course, wintertime, we're looking back this way. Those pink regions, let's just circle a few of them here, are very typical, what we call emission nebula. And I'm sure you guys have all seen photographs, or rather images, artists' impressions of like this, and you think, what are all those pink areas referring to? And they're referring to what we call emission nebula. So let's go and have a closer look at that. And that's really a typical close-up image of a typical, what we call an H2, or this ionized hydrogen emission nebula. And when you start getting star formation, the biggest stars always occur first. Why? What is the main driver of new star formation? Gravity. So if you're getting clumps of bigger clumps and lots of smaller clumps and so on, the bigger clumps have more mass, so there's more gravity driving them. So that star is going to get up and running a lot quicker than these smaller ones down here with lower mass. So it's the big stars that get up and blazing first thing when you get these regions of star formation. Because they're big and they're massive, they're generating large amounts of energy, and they're giving out huge amounts of ultraviolet, high energy ultraviolet light, as opposed to, say, our sun, which is predominantly giving out wavelengths of light in our sort of visual or optical wavelengths that we're used to, which is not so powerful. But these big stars are predominantly blazing out in high energy ultraviolet light. And the ultraviolet light then goes to the hydrogen that's out there in the gas and dust that hasn't had a chance to form into stars yet, because these big ones have got up so early. And it what we call ionizes them, bumps an electron off. The electron then naturally wants to fall back to it, and when it does, it emits light in the pink-red part of the spectrum. It's called fluorescing. Essentially, it's fluorescing. So you get the hydrogen that's fluorescing, and it always has this red-pink appearance to it. So when you see these sort of images, that's what you're looking at. It's a region of early star formation. Massive big stars are blazing away ultraviolet light and making the hydrogen around them to fluoresce. And that's what all those little pink areas are about. Let's have a look at the Orion Nebula. Everyone's sort of hopefully seen the Orion Nebula. If you haven't, it's just a beautiful thing to look at in summertime. Looks gorgeous. Let's have a closer look at that here. And it's exactly what's going on. There's the trapezium set of stars in here. All these stars here are big, massive, bright stars, but in particular, there's the trapezium cluster of stars here, big, bright ones. They're blazing out ultraviolet light, and they're causing all this hydrogen gas around here to fluoresce. So that's what you're looking at when you're looking at the Orion Nebula. Okay, so let's have a look at our modern measurements. I've alluded to some of them already. So first of all, how many stars we're looking at? Roughly estimate about 400 billion stars. I think, sort of a rough guesstimate. I think the Milky Way has probably got in it. From here to here, the diameter of the disk, about 100,000 light years across. That's how big the Milky Way is. Remember, 1 light year is 10 million kilometres. So it's about 100,000 light years. We sit out here halfway out, and we're about 26,000 light years from the centre of the Milky Way. So we're about halfway out very roughly. The thickness of the disk is about 1,000 light years. Give you an idea of that. And here's the nice big central bulge here. And it's got a mixture. The central bulge, let's talk about that now, that has a mixture of young and old stars in random orbits. So the disk around here is new star formation, so that's predominantly, not all, but predominantly young stars, and they're all rotating around in that disk, as opposed to in the central bulge, you've got a mixture of young and old stars, and they're just, a good way to describe it is like a beehive. It's just, so everything goes around the orbit. Never lose sight of that. Everything orbits the centre of the Milky Way. So they are orbiting around it, but they're just coming in from all directions. You might have stars doing that, and stars doing that, stars doing that, stars going in from this angle. From almost any orientation you can possibly think of, you've got stars just zooming in and going around the centre of the Milky Way, or the centre of that bulge, essentially, and back out again. So it's just a chaotic sort of random orbits, and that's what's going on with old and new stars. Very, very dense region. And that's why it looks very swollen and it looks very bright. Okay, so the galactic bulge, so from here to here is roughly, the spherical component of the bulge is about 10,000 light years across, to give you an idea of its size. And as I mentioned, 2/3 of spiral galaxy have a bar structure running through the middle of the bulge. And the galactic bar in the Milky Way is about, the length of it's about 27,000 light years long. What causes the bar, I don't really know, but I know with computer simulations, a bar will form in about 2/3 of galaxies anyway. If you just get that whole motion of going around, it just seems to be something formed. I don't know if they have nutted out exactly the reasons, the mathematics behind it, but it does seem to happen. And the bar is thought to provide an important method or facility to bring stars in from the disk and bring them into the central bulge, and that's how you get your young stars in there too. The bars seem to play some sort of role in that.
Do they understand why you get the spiral arms? Is that understood why you actually get those arms?
Yes, yeah. Well, it's still, Yeah, now I'm forgetting the guys, the two Japanese guys who came up with this theory. It's a because normally you would think that they would just get tighter and tighter and tighter, but they don't. And that's where they came up. Hang on a minute, these are really slow moving pressure waves. They're not actually waves of stars, it's just waves of pressure. And once again, that's really complicated, a load of mathematics behind that, and it's all hypothesized and so on. And that's why they've suddenly realized if they were just spiral arms of just material, they would slowly get tighter and tighter and wound up, like a spiral arm in your coffee. Give it a stir, it just gets tighter and tighter. And that's why they think it's most likely these pressure waves that are going around.
How can you have pressure when it's kind of in a vacuum?
Oh, gravity. What's driving the pressure waves? Gravity.
Oh,
yeah, gravity drives them. Yeah. And I don't think it's all that simple. I'm sure there's a lot behind it yeah. But good question. That's a good question you think about. What's driving all those things? And yeah. Okay, so we've talked about, yeah. We're going to talk about that, yeah. Yep. So we're still discovering, we're still on our journey together, discovering, yeah. So we've talked about the disk, we've talked about the spiral arms, we've talked about the bulge, we've talked about the bar. So this lady here, Vera Rubin, an American astronomer, she made this extraordinary discovery, which is still to this day one of the key evidence for these things called dark matter. What is dark matter? Dark matter are hypothetical particles that interact with other matter through gravity, but they neither emit light or it doesn't absorb light. So you can't detect it with any form of light. So they're just essentially invisible to us in terms of light, hence the name dark matter. You can't see it, but you know it's there through its effect on gravity with other matter.
So, quick question. So, light means all sorts of light, but light?
Yeah, correct. Radio waves, infrared waves, light waves, X-rays, gamma rays, all forms of electromagnetic radiation.
Right.
Probably I should use that word, electromagnetic radiation. It doesn't absorb it, it doesn't emit it, so it's just invisible as far as light is concerned, but it does interact through gravity. Also through the weak nuclear force, but that's minor detail, yeah. So it's time to go on our extraordinary discovery of dark matter. So what Vera Rubin did, she picked out a handful, I think it was about 60 in total, of spiral galaxies. And using the technology of looking at the hydrogen gas and the way it was moving and the Doppler effect, she studied the motion and the velocity, how fast this gas was going around with each of these spiral galaxies. And this is one particular galaxy here called the Triangulum galaxy. It's in our local group. It's the third largest spiral galaxy. It's a little bit further out, so it's a little bit over 2.5 million light years away from us, but it's a lovely example of a spiral galaxy. And what she did, so I've put here, she formed some data, and we've put the graph over the top. So on the horizontal line, from the centre of the galaxy going outwards, the distance of the gas and stars as you head out, plotted against the velocity or how fast they were moving. And you'd naturally expect, under the normal laws of physics, that as you get further out, you got less gravitation, you got less mass, so you got less gravitational influence, so things are going to move a lot slower. Much like the planets, the further you go out in the solar system, the planets are moving slower and slower around, and that's what you would expect. And this graph here would show this is what you'd expect. But look what they observed. So, it started leveling out and then actually started to rise. All the gas, long after the stars, the velocity of the stars was quite high, but long after you could see any stars, all the hydrogen gas was still going out at increasing velocities. And that only means one thing. There's mass out there. And so that was one of the key evidence for dark matter. So it was from there they concluded that galaxies do have a lot of dark matter in them, and this is the Milky Way's dark matter halo. So when we looked at this sort of the stellar halo, which was a sparse collection of old stars and the globular clusters, and they were all sort of a spherical arrangement circling the disk of the Milky Way. But the Milky Way, what we can see is then in turn embedded in this much, much bigger spherical halo of dark matter. Size-wise, it's thought to be 600,000 light years across the spherical halo of dark matter. Remember, from here to here is about 100,000 light years. Here to here is about 600,000 light years. Massive. 95% of the mass of the Milky Way is thought to be dark matter, this hypothetical particle. Okay, here we go. here's your supermassive black hole. So that's covered the dark matter halo. So the centre of the Milky Way galaxy, once again we've used the image here of Andromeda, but the centre is known as Sagittarius A star. Sagittarius refers to, it's in the constellation of Sagittarius, and there it is, that's the Milky Way, that's the big disk we looked at earlier on, side on. So it's in the constellation of Sagittarius, and the A plus refers to that it's a strong radio source. And your radio telescopes that I mentioned came into sort of being about 1930s or so. And it was this guy here, Karl Jansky, in 1933, was the first guy to identify that right from the centre of the Milky Way, the constellation of Sagittarius, something's going on there that's emitting it's been a strong source of radio waves. He is considered the father of radio astronomy, and just have for newtons for force and so on, and a lot of your units are all by famous people. The unit that they use in radio astronomy is the Jansky, and that's because of Karl Jansky. He only lived about 45, a very sad and timely death. So what was going on? Once again, because all the gas and dust, looking back at the centre of the Milky Way, they had no idea. We couldn't see way back then. And it was these two people here. There's a German astrophysicist and his team, Reinhard Genzel, and Andrea Ghez, an American astrophysicist, and her respective team won the 2020 Nobel Prize in Physics because they were the first people who actually gave strong evidence of what is going on at the centre of the Milky Way. So their observational research was in the mid-90s when new technology came forward. What was that technology? 3 things that gave them the tools to find out what was going on from this radio source in Sagittarius A+. Large telescopes, we're going to look at each of these shortly. Large telescopes, infrared astronomy, and adaptive optics. So let's have a look at them. First of all, large telescopes. A whole new generation of large telescopes, such as the Keck 1 and 2 observatories here, 10-metre primary mirrors, 10 metres. Whoa, size of this room, huge, huge mirrors. So if you increase the size of the mirror, you're catching more light, which means images are more brighter, so you can see fainter objects, and you can see them with greater resolution or clarity. So that's a very, very important thing. So the new generation of large diameter telescopes. Infrared astronomy. As I mentioned, our eyes can't see infrared. It's the same with the early detectors on telescopes that were designed for the visual wavelength light. So with better technology, they developed better and better sensors on their telescopes to pick up and record infrared wavelengths of light that can penetrate dust, get through the dust. Stars emit in infrared wavelengths. They emit in a whole range of wavelengths, including infrared. So if you able, these huge big telescopes, with an infrared sensor on your telescope, you're able to cut through the dust, penetrate through it, and actually have a look what's going on the other side of that dust. The third one is adaptive optics. And what they're able to do, that's what this refers to here. So there's, as you know, high in the atmosphere, there's always a lot of turbulence going on up there, and that distorts your light. So the technology here is they get lasers, they shine up and they excite sodium atoms high in the atmosphere. They're then able to observe and record the disturbance that's occurring in those sodium atoms. That feeds back to the telescope, and that we're talking splits of seconds, remodel and re-alter the shape of the mirror. We're talking many times per second. The telescope mirror is just adjusting itself to counter the atmospheric disturbance. Amazing technology. So it's called adaptive optics, and it's able to counter all the turbulence that's going on high in the atmosphere. So it was those 3 really big things that started coming to life in the mid-90s, these guys. And what they studied, they could see some stars cutting through the dust. In particular, they were able to look at the orbits of 6 stars that are in the centre of the Milky Way and look at the orbital properties. And let's just have a look at this here. So here's a little model here. Here's the centre. We've got the star. And look at these. Let's just look at this one here. It goes around and it's zipping around something, going back. These stars are really high velocity. See down here, they're zipping around. And that tells you, when you calculate the velocity of a star in its orbit, and you can see its position, you can see where it's going around something. It's relatively straightforward mathematics to work out the mass of the object that they are going around, and that's what they were able to do. And what they concluded, that these high velocity orbits of these 6 stars were orbiting that point, radio source, Sagittarius A star, implying it was orbiting an object. The mass they calculated was at least 4 million times the mass of our sun. And it was very compact. It was no larger than the solar system. Whatever it was no larger than the solar system, which in the big scheme of things is not very big. So that implies it's a really supermassive compact object. There's only one thing it can be, a supermassive black hole. And a black hole being where you've got something really dense and compact, high mass, it's really dense and so compact, whereby the gravity around it is so powerful, not even light can escape. And that region at which light can't escape is known as a black hole, and the boundary of which is called the event horizon. You've probably heard of that term. So they concluded that is a supermassive black hole, and they won the 2020 Nobel Prize for that. Having a closer look now, the 2022, you may have heard of the Event Horizon Telescope. That's where they got a network of about 8 radio telescopes all dotted around the globe, and they connect them together with calculations, with complex computers and so on, such that they behave as one massive big radio telescope, the full size of the Earth. So once again, bigger size, better resolution. And it's in radio waves, and this is what they saw, the first direct evidence of the supermassive black hole. And let's just blow this up so it's revealing the shadow. Here's a picture of it here. So here's your black hole in here, and this is particles, heated particles racing round and round here, the region of the black hole, and when they do so, through the process of what they call synchrotron radiation, they emit radio waves, and of course it's being picked up by the Event Horizon Radio Telescope. To give you an idea of size of things here, here's your event horizon, the black hole is all in the middle here. That there is Mercury's orbit in our solar system, and that's around here. This region here, the event horizon from here to here, is about 24 million kilometres. And you know, in space terms, that's next to nothing. It's so compact. And that's your event horizon. So the little object in there is tiny, 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 right in there. You can't even see it. But the region of space around it is just 24 million kilometres. So here's Mercury's orbit. You know, Mercury's the closest planet. It's got an orbit of about, I think about 68, million kilometres. So it's out to about here, and right in here is about 24. So it's sort of, you know, a third of the size of the orbit of Mercury. So it's very, very compact. So there's your supermassive black hole in the centre of the Milky Way. So let's sum up from here. So what you've got here is you've got your nice central bulge. You're looking straight down and all side on here. So here's your central bulge. You've got your bar here. You've got these spiral arms of new star formation with big massive stars and then lighting up, fluorescing all the hydrogen around it here. We know we're about 100,000 light years across. The sun, we're sitting about halfway out, which is out here. And your supermassive black hole, that's got the mass of at least, I think the latest calculation is about 4.2 million times the mass of our sun, sitting in the middle here. And all of that is embedded in a large dark halo of dark matter that extends way out here, of diameter of about 600,000 kilometres, light years rather. And that's the Milky Way, our home galaxy. Thank you. Thank you. Now, any questions, Rex? Would you?
The relationship of dark matter to the black hole, is there any knowledge or evidence that the black hole contains dark matter, or is it a separate? Do we know?
Yeah, good question. So is there dark matter within the black hole? Dark matter seems to permeate throughout the whole galaxy, so I'm sure there will be dark matter associated with that. I would expect so, because you've got something pretty mass attracts matter attracts matter.
Dark matter has gravitational properties, so one would expect it would be attracted into it.
In fact, I remember asking that of a guy, the Australian astrophysicist, cosmologist who came out here, Razin's conference, 2017. I asked him that exact question in the evening over dinner, and he said it seems to be that yes. Remember what I'm saying? He said if you can imagine the dark matter distribution goes like that, and it does seem to rise at the centre in that central bulge, because matter attracts matter. Yeah. It's a good tracer. Normal matter, visible matter, is always cosmological terms. You know, when you see the big filaments, and I think the last talk we did, you know, all the cosmic web, and you see all the visual of all the galaxies and stuff, and that's a wonderful tracer. Visible light is a wonderful tracer of where dark matter is. Out of matter across the whole universe, about 85% of it is dark matter and 15% normal baronic matter that we see, and that 15% is a good tracer of where that invisible dark matter is. So it makes sense. Good question. Yeah.
Well, once it's inside the event horizon, though, it's all over.
It's all over. Yeah. It's all over. Yeah.
If you look at a black hole with a radio telescope, do you really see it emitting anything?
Well, you don't see anything, hence the shadow. You don't see anything from the inside the event horizon, because light can't escape from there. But as it showed, you see all the light coming from the particles around the event horizon.
What's the one that ejects, you know, like, because when we had that other guy, I think he's Sergey, he showed us like the radio telescope and it would pick up, you know, that big emissions jet.
X-ray jet.
That wasn't a black hole.
Those jets come from the accretion disk,
Yeah.
not from the black hole itself.
Yeah, correct. Yeah. So that's a whole different talk on that's a whole talk on massive black holes and bipolar jets of material shooting out, and they're emitting radio waves when they do that. So that's different here. You would see that if our supermassive black hole got active and you gave it something to munch on, a whole big stack of gas and dust and stars, and you threw at it, it would form a nice big thick accretion disk and whirl into action and start shooting out bipolar jets of material, and that material would naturally give off radio waves, and that's what you're seeing in big lobes on either end.
It's not coming from the black hole at all.
It's not coming from the black hole, it's coming from jets material coming from the accretion disk and bipolar. And a really good analogy of a black hole is like a volcano, how they can just lie dormant and then they can come to life again. And early when galaxies were more dense and congested, most of those galaxies, all their supermassive black holes were active. And you see them now, telescopes are called active galaxies or active galactic nuclei. And you see these big polar jets of material shooting out that's emitting radio waves. You get these big lobes of radio waves. But our supermassive black hole intermittently gives a bit of a splutter, of a little bit of a, nature throws it a biscuit every now and then, a little bit of gas cloud goes past and it goes splutter, splutter, splutter. But essentially it's dormant, because we're a more mature galaxy and a lot of the stuff's already been used up. So I hope that answers your question. Yeah. Yep.
I have a question. So the Andromeda galaxy, I saw two other galaxies next to it, probably M32 and M110. Are they satellite galaxies of Andromeda?
Oh, yes, the picture of the Andromeda Galaxy. Yes. That image, that beautiful image of Andromeda Galaxy, you see the bright spots. Yes, they are satellite galaxies, just like we've got the large, small Magellanic Cloud galaxies and the Sagittarius dwarf galaxy and the Canis Major dwarf galaxy. We've got them too, and Andromeda's got them, which you could see beautifully.
What are the elliptical galaxies?
No, they're usually irregular galaxies, they're little tiny dwarf ones. They just looked that way. They looked that way. Now, incidentally, since you've picked up a little bit of detail in that image, hey, this one here, can anyone tell me what these little objects are? That's Jupiter and that's Antares. Just a little bit of trivia, throw that in there. Yeah. Just since you picked up on that little bit with Andromeda. Now, I think there's a question over here. Andrew. Yeah, we'll get you both. Yeah, Andrew. Yeah.
I was just going to ask, is there anything on the age of the galaxy? Because it's about double the age of the Sun and the Earth.
Yes, correct. What is the age of the Milky Way? And the evidence seems to suggest it's a fairly early galaxy. It's almost as old as the universe.
Really?
Yeah, it's almost as old as the universe. It's one of the very first galaxies.
So the follow-up about it is it's quite curious that it hasn't burned through all its gas.
Yeah, correct. Because it's still gobbling up and absorbing your irregular galaxies, your satellite galaxies. It's had a lot of mergers. How do they know? They can actually trace it back through the data from the Gaia telescope, or satellite rather, that is able, and it's able, you know, I mentioned it can see groups of stars of certain ages and compositions all moving together, and they can trace that backwards with their supercomputers, and they can actually date and time roughly when certain mergers have occurred. And so there's actually some, I don't carry all the detail up here, but it's fascinating reading about the history of the Milky Way. The archaeology of the Milky Way is quite fascinating, and that's how they do it through the Gaia data. Yeah, so really, but yeah, it's almost as old as the universe, as the Milky Way galaxy. It wouldn't have looked nothing like what it is now. It's evolved this way. Yeah. Yes, gentlemen.
You said there's 400 billion stars in the galaxy. The supermassive black hole has a mass of 4 billion stars. Why is it so small?
Which is what's small? Sorry, the
supermassive black hole in the
it's so condensed. Yeah.
No, so why is it so small? There's 400 billion stars in the galaxy.
Yes.
Why hasn't it gobbled up more of them?
Oh, because the distance further away. Because often this thing people think, oh, these supermassive black hole just sucks everything in. You've got to be reasonably close to it, because remember, gravity is G, 2 masses over r square. So the further you get out, the gravitational force drops away. And the other thing is everything's rotating. So it's going around the centre. It's not just heading straight in. Whereby, if you turned the sun instantly to a black hole, just hypothetical, apart from the obvious, we'd lose our light, but just we're talking hypothetical here. If you did that, the Earth wouldn't suddenly whoosh into the black hole. It would just carry on. The Earth, gravitational-wise, as far as Sir Isaac Newton knows, just travelling around, and Einstein for that matter as well, with the gravity wells and that, as far as the Earth is concerned, it would just quite happily continue just to go around. It wouldn't notice anything different. The same mass is in the same spot. It's just that if you got really, really close to it, but Earth's not, because it's in a nice orbit around the sun. So all those stars orbit the centre. They're in orbit, they're a long distance away, and they're orbiting around it. They're not heading straight towards it. So that answers your question. Yeah. Well,
is it true that if you get close to the centre of the galaxy, it's uninhabitable for human life?
Yeah, just like there's the habitable zone for around stars for a planet where there's liquid water, not too cold, not too hot. There's habitable zones or ideal Goldilocks zones for galaxies. In the centre of, right in that dense bulge, there's just too much activity. It's too dense. There's big gamma rays. That's downtown. It's just crazy stuff going on. Gamma ray bursts. It's too many stars, big stars next to you and stuff. It's just not really conducive to life forming, or certainly life forming in a planet.
If you got too close to the sun, like if Earth was too close to the sun, it would suck it in, just like Jupiter, kind of like. Because one time they had a talk, and it was talking about the comets that go around, or the asteroids. I get them mixed up, but how Jupiter sucked in most of the asteroids because of its mass. Yeah. So it's kind of like, if we were too close to the sun, then the sun would just suck us in.
But that's not going to happen, because we're in an orbit. We're in a stable orbit. Now, earlier in the solar system formation, when orbits were unstable,
you just orbit around it unless you get too close. Yeah. And also, when you have a star, I remember one person said that like 95% of it gets recycled. Like the hydrogen and the helium, it gets recycled, kind of like, because when it explodes,
supernova explosions. Yeah.
It doesn't eat all of the hydrogen and the helium. It just kind of like goes off, and then it gets recycled.
Correct. Yeah.
So it takes a long time for that to happen. That's why. Yeah. There's still lots left over for it to happen.
Yeah. Correct. Yep.
Chris?
Yeah, Andy.
I wanted to ask something. I was talking to my son about the size of the Milky Way being 100,000 light years.
Yes, correct.
Quite a convenient number.
Yeah.
Round number.
Yeah.
And Andromeda being, what was it?
It's about 40% bigger. So it's about 140,000 light years across the diameter, roughly.
So has there ever been any thoughts of using like a unit which is one like Milky Way?
Yeah, sure.
And saying the distance away is so many Milky Ways, like a galaxy unit? Sort of thing?
I think galaxies all differ slightly in their sizes and stuff. whereby it's not a practical thing to compare galaxies like that, but also there are already some units like the parsec. You know, astronomers tend to use the kiloparsec. They find that much more convenient, and it's more mathematically deduced.
I'm thinking more in terms of communication to
Sure.
a younger audience, etc.
Which case you can, when you're trying to talk to a younger or general audience, you can probably, to be honest with you, could probably use what you find intuitive, people latch onto, and there'd be nothing stopping you from saying, well, the Milky Way is 100,000 light years across. The Andromeda is 40% bigger, so it's one. So it's,
but then also the distance away is like 25.
Well, you're talking 2.5 million light years. You're talking 2.5 million light years. So
that's 25 galaxy units away.
Yeah, but
25 galaxy units.
So if you wanted to do that, that's fine. But astronomers find it a lot easier to talk in kiloparsecs. They just find it easier, and because the parsecs all based on trigonometry is how it's based on. Yeah.
We do something similar to that though in the solar system.
Yeah. The astronomical units. Yep, exactly. The distance from the Earth, but that's used within this.
In terms of what you can understand.
Yeah.
Like we pulled out a tape measure.
Yeah.
So let's say 1 centimetre is a galaxy unit.
Sure.
One
Yeah.
Milky Way.
Yeah.
25 centimetres away is the Andromeda galaxy. Excuse me, can I just finish? And then a certain amount of distance away, like about 2.5 metres, is like the I think it was the Whirlpool galaxy.
Yeah.
So you can't go,
I think that's a great
scale model of
galaxies. That would be brilliant. Absolutely, you could do that, and you often do that with the solar system. There actually is a scientific unit, but that's a brilliant idea, and you could do that in a talk and say to give you an idea of how close things are, how far apart. Absolutely, yeah, absolutely, Andy, absolutely.
How far away did you say Andromeda was? How many light years?
It's 2.5 million. Roughly.
2.5 million.
Yeah. So now look, that's great. You can use all those sort of things, absolutely, and it's a good one for audiences to put things in perspective, how close and far away things are at. Absolutely. Yep.
So it made me think that like Andromeda, for instance, in terms of the size of our galaxy, isn't that far away compared to say the size of the sun and the nearest star. Like chalk and cheese.
Yeah, absolutely. Yep. So yes, you could do that, absolutely. Yeah. Because I hear what you're saying. Astronomers might use their little thing, that's fine. But could I do this as a conceptual thing? Absolutely. And even astronomers use as Bill alludes to within the solar system, the distance from Earth to the Sun, about 150 million kilometres. They call that one astronomical unit.
Yes, exactly the same thing with a galaxy unit.
Yep, so Neptune, for example, is 30 astronomical units.
Exactly.
Yeah, as opposed to 4.5 billion kilometres. Yeah. So absolutely. Yep, you could do that, Andy. Absolutely. Yep. That's your idea. Yep.
Actually,
Give you credit.
my son's as well, because he brought the name.
Well,
and it came from astronomical unit.
Yeah. What shall we call it?
Galaxy unit.
Galaxy unit. There you go. GU. No, look, honestly, that is a good conceptual idea for audiences. Yep.
Heard it here first.
Yeah, heard it here first. No, good on you. Thanks, Ed.
I've got something, a puzzle that people can look into if they can't answer it tonight. Which year was that photograph taken? And there's a clue there that in 2019, based on the position of Jupiter.
Oh, right. Oh, okay. Yeah. Good one. What's the answer? 2019. 2019. There you go. Yeah, cool.
That was when Jupiter was last in that part of the sky.
Cool. Okay, otherwise, no other questions. That was here. Bit of fun, so that's all good. So thank you very much, guys, for coming out, and we'll see you next month.
Photograph of the Milky Way on the wall there on the wallpaper, which was taken by Society member Abbott Campbell, who's the guy who runs the astrophotography competition. So they had his image of the Milky Way printed on the